So I just wanted to continue with these concept bite videos. This one's on fluorescence, which you should all be reasonably familiar with. Here I've just got a simple Yablonsky diagram, and around it I've listed all of the transitions which can occur within a molecule. We start with our allowed transitions. These are things like singlet-singlet absorption or fluorescence emission. So fluorescence is emission from an excited singlet state to a ground singlet state. I can also have internal conversion, which is commonly referred to as vibrational relaxation. I've then got my forbidden transitions, where I have a singlet triplet absorption, which is forbidden but still can occur, but it will occur at very, very low intensity, very low extinction coefficient. Then I have my emission from my triplet state to my ground state singlet, which we call phosphorescence. And I have intersystem crossing, which is just my internal conversion, my vibrational relaxation from my triplet state. To populate my triplet state in the first place, I have intersystem crossing. This just is my singlet going into my triplet. And I've demonstrated each of these cases here. So I can have just singlet absorption. I can have vibrational relaxation. And I really can't manage to get my triplet absorption. It's very low intensity. But if I have a triplet, I can have vibrational relaxation, and then I can have internal conversion and vibrational relaxation down in my intersystem crossing. Whenever there is a change of spin of my system, it's an isoenergetic process. In other words, it goes across, horizontally across on my energy level diagram. So, fluorescence. Here I've got an absorption and a fluorescence spectrum, and we can see that the fluorescence spectrum is essentially a mirror image. It's at lower wavelength because I have my Stokes shift, which lowers the energy gap between my ground and my excited state. And I have this is just showing the absorption and the emission spectra of this molecule here, YoPro1. It's just a fluorescent molecule. But important things to note about fluorescence is that we always see fluorescence from the lowest vibrational energy level, and we always see fluorescence from the lowest excited state of a given spin multiplicity. So I see fluorescence from S1 levels or T1 levels. Because vibrational relaxation occurs very quickly, we're talking 10 to the minus 12 seconds, whereas phosphorescence occurs at a much longer time scale. So things have had time to vibrationally relax before they've had time to lose light from fluorescence or phosphorescence. Here I've got the Kasha-Vavilov rule, which continues on from Kasha's rule, which is the previous one, which basically says that the quantum yield is independent of the excitation wavelength. So I've got a slightly different molecule here. I have rhodamine 6G, and on the left I have the absorption spectra, and the right I have the emission spectra. And you can see I've got three different emission spectra here, all measured when excited at three different wavelengths. So we can see my pink line on my emission spectra is excited at 530. That's right at the top of its absorption peak. The green line is at 500, which is just on the shoulder, and the blue line is at 345, which is again much lower. However, if I normalize any of these lines by dividing it by the absorption at the excitation wavelength, all of the emission lines will overlap. This is an indicator that quantum yield is independent of my excitation wavelength. And so fluorescence spectra are independent of my excitation wavelength. Now, with all things, particularly in photochemistry, where we have our selection rules and things, they're more of guidelines, and there is an exception to this rule. This exception to particularly Kasha's rule, where we see this emission from the S1 state, in azulene. Azulene's a very important molecule in photochemistry because it's a molecule that we still don't fully understand. But azulene sees emission not from its S1 level but from its S2 level. The reason for this is that there is a very, very large energy gap between the S2 level and the S1 level, and so the rate of internal conversion, the rate of vibrational relaxation, is very, very slow, and this gives the molecule time to fluoresce from this S2 level. Azulene, however, is unusual. Almost everything else will emit from the excited state singlet. From the first excited state singlet or the first excited state triplet.